Hello everybody, and welcome to exercise 1 on page 49 of the workbook. Let's work through this example together and just start by reading it. So, a rope that's 20 meters long and that has a uniform density of 1.5 kilograms per meter is hanging over the edge of a steep sea cliff so that the bottom edge barely reaches the ground. Okay, and part A would like us to figure out how much work is done in pulling the rope to the top of the cliff. Okay, so this problem is very similar to an example that we worked earlier in the section. Let's start off with a picture here. Okay, so we've got our nice sea cliff here and rope hanging over the edge here. And we sort of have the same issue in this problem that we did in the previous example that we worked, and that is that not every portion of the rope has to move the same distance. Okay, the part at the very bottom has to move farther than the point in the middle, for example. Okay, so we approach that difficulty by just thinking of breaking the rope up into pieces, taking a slice of the rope, and just thinking about how much work it would take to move that slice up to the top. Okay, a distance of y. All right, so think about the two components that are involved in work. There's force and there's distance, and in our case, force is about finding the weight. Okay, so the first thing we'd like to lay our hands on is the weight of the slice that we just drew. Okay, just of the slice of the rope, not of the entire rope, just of that one slice. Okay, and as before, we discovered that we can break that down into three components: the density times the length of the slice times the acceleration of gravity. Okay, let me buy myself a little space here. Okay, let's do just a brief units check to make sure that we believe those three pieces are going to work. So density is going to be mass per unit length. Okay, length is going to be in meters, and acceleration of gravity is going to be in meters per second squared. Notice that meters cancel, and we get kilogram meters per second squared. That's a Newton, which is the correct unit of force in this case, okay, or weight. All right, so what do we have for these three pieces? Well, notice that in this problem, they give us the density directly, 1.5 kilograms per meter. We don't even need to calculate that. Okay, I think in the previous example we had to calculate that, but here we are given that number directly as 1.5. Okay, the length of this little slice is just going to be dy, because we're thinking of it as a really short slice of the rope that we're talking about. Okay, an acceleration of gravity, 9.8 meters per second squared. You can take those and multiply them together. 1.5 times 9.8 is 14.7. Okay, so 14.7 dy newtons, that's the weight of just this one little slice of the rope. Okay, so besides weight, what is the other component that's involved in work? It's the distance that that slice has to travel. And we can see from our picture that the distance to get to the top is y meters. Okay, and so to get the work, we need to multiply weight times distance and then integrate to add up the work of all of the slices of our rope. So if we put that all together into one integral, we're going to take an integral of our weight times our distance. Okay, so 14.7 y dy, and the last thing is what would the limits of integration be? Well, we move from the top of the rope to the bottom. We're going from a distance of y equals 0 to a distance of y equals 20, and that tells us that our limit should just be 0 to 20. Okay, and we're ready to do the integral. So let's see, antiderivative of y would just be y squared over 2. We'll evaluate that between 20 and 0. Okay, and then let's see. We substitute in 20 for our y. We're going to get 20 squared over 2. Lower limit's just going to be 0. Okay, you can double check my calculations and confirm that that works out to be 2940. Okay, and last thing, what units do we have here? Well, we've got newtons times meters, so we should be getting joules. Okay, and there is our answer to part A. So let's move on then to the second part of this. Okay, so what are they asking us in part B? So a surfer of mass 85 kilograms is stranded by high surf on a beach beneath the same cliff that we just talked about. How much work would be required to rescue the surfer by pulling him up over the top edge of the cliff? Okay, assuming that he's firmly attached to the rope, that would be good. All right, so how do we think about part B here? Okay, well, basically it's very similar to part A with the one difference that instead of just the rope, we've got the surfer kind of attached at the bottom. Okay, so one way to think about this is to say, well, the total work that we're going to do here can be broken into two pieces. It's going to be the work that we need to move the rope, okay, plus the work needed to move the surfer. And the thing is, we already know what the work needed to move the rope is. We calculated that in part A. That's 2940 joules. So all we really need to figure out is this. How much extra work does it take to move the surfer to the top of the cliff here? All right, well, to move the surfer, all we really need to do is to take the surfer and get him to the top of the cliff, which is a distance of 20 meters. He is going to move the entire 20 meters that we're talking about. Okay, so the only question then is, what is his weight? That's the force that needs to be moved that distance of 20 meters. All right, so let's go down below and just do a couple of side calculations here. So the weight of the surfer is going to be his mass, 85 kilograms, times the acceleration of gravity. Okay, what does that turn out to be? I need to pull out my calculator here and see. Okay, so 833 newtons. And to turn that weight into a work, we just need to take that 833 newtons and multiply by the distance that it's moving. Okay, so what we're going to do then is go back up here and fill in that missing piece. So the work needed to move the surfer is just going to be the product of these two numbers, 833 times 20. Okay, and let's see. That's 1660. 16,660. Okay, and so to finish the problem, we just need to add those two things together. And you can double check my calculation. I got 19,600 joules. Okay, that should be our final answer. Okay, and I think we have finished the problem.